This is the 7th lecture on my series on thermodynamics. In the lectures so far, we have met the 0th and the first law of thermodynamics. We found that the 0th law states that thermal equilibrium is a transitive property, and this led to the notion that temperature exists. Now, we just met the first law of thermodynamics in the last lecture, and there it was stated in the following form: work done under adiabatic conditions is independent of the path taken. Now, just like the 0th law implies the existence of temperature, this version of the first law actually implies the existence of a thermodynamic quantity that is known as the internal energy. Now, before we go into how the statement of work done under adiabatic conditions being independent of the path leads to the concept of the internal energy, let me briefly remind you something we have also covered earlier in this series. Basically, a quick recap of some concepts which we borrowed from mechanics as far as work is concerned. Now, mechanical work is a line integral of the force acting on a point particle dotted with the displacement and integrated over the path which the particle takes. This is, of course, for a point particle. This result can be generalized to a system of particles as well. Now, what is very important here is that mechanical work is usually path dependent. However, for special kind of forces called conservative forces, work done happens to be independent of the path, and this actually leads to the concept of potential energy in mechanics. Now, you can see the parallel here. In thermodynamics, work done is usually dependent on the path. For a hydrostatic system, where work done is the integral of PdV, the area under the PV curve, that of course depends on the particular path taken to go from a state PIVI to a state PFVF. However, as we have just stated, the experimental evidence shows us that under adiabatic conditions, work done is path independent. This is, of course, the first law of thermodynamics. So just like work done for conservative forces being independent of the path leads to the notion of potential energy, here we expect some kind of energy which is a feature of the system that is lurking behind the statement of the first law. The independence of the work done from the path in the case of adiabatic processes. This is actually what we use to introduce the notion of internal energy, as we are going to explain now. Using the fact that work done under adiabatic conditions is path independent, we can do the following. We choose a standard state P0 of a system. The state could be anything that we like at the moment, and take the system adiabatically to a state P from P0. Now, the work done in the process will depend only on P and not on the path taken. Of course, it will also depend on P0, but while we will allow the state P to change and in fact range over all the states possible of the system, P0 will be taken to be a fixed state, so we are not going to talk too much about the dependence on P0 at this stage. Now, we can use the fact that this work done is independent of the path taken to define a state function. A function of the state alone, that is a function of the thermodynamic parameters which describe the state, and not on the history of the state, not on what happened to these thermodynamic parameters before you reach this particular equilibrium state that you are currently in. Now, this defines what we call the internal energy. Basically, the internal energy of a state P can be defined as negative of the work done under adiabatic conditions to take the system from P0 to P. The negative sign here is simply a reminder or simply analogous to the negative sign that we have in the case of the definition of potential energy from the work done in the mechanics. There too, the potential energy is defined to be the negative of the work done by a conservative force to take a point particle from some standard initial position to its current location. You can see the parallels here. Work done under adiabatic conditions, which is the path independent thing, from P0 to P with a minus sign is defined to be the internal energy of the system in the state P. Of course, if you talk of another state Q, as you can see in this diagram, then the internal energy of the state Q is given by the work that you would have to do to go from P0 to Q under adiabatic conditions, again with a minus sign in front. And note that the path could be the one that I have drawn, but could be anything else, could be something like this. As long as the path is adiabatic, you are actually going to get the same work done and hence the same value for UQ, irrespective of the path chosen. Now both UP and UQ of course depends on the choice of P0, which is something you have made arbitrarily. But let us look at what happens when you try to move from the state P to the state Q by some adiabatic path again. Now this adiabatic path from P to Q could be 1, but you could think of another adiabatic path, a path which goes from P to P0 and then on to Q. So this is that path, and according to the first law of thermodynamics, these two works are one and the same. But when you take the system from the state P to P0 and then to Q, the net work done in the process is simply a sum of the work you do when you move from P to P0 and then from P0 to Q. So the sum of these two terms. Now, work done under adiabatic conditions when you move from P0 to P with a minus sign happens to be the potential energy here. But what we have here is the work done under adiabatic conditions to move from P to P0. There of course has to be the negative of the work done under adiabatic conditions to move from P0 to P. So just by using the definition of UP and consequently UQ, this expression simply becomes plus UP from here and minus UQ from here. So the work done under adiabatic conditions to go from P to Q is UP minus UQ. That is negative of the increase in the potential energy, decrease in the internal energy. So under adiabatic conditions, the work done to go from P to Q is simply the decrease in the potential energy between P to Q. That is minus delta U P to Q. Now this of course depends only on the endpoints P and Q and not on the path. It is also independent of the arbitrarily chosen state P0. Now the fact that it's independent of the arbitrarily chosen state is pretty easy to figure out. If instead of P0 you had chosen P0 prime as your arbitrary state, then the work done could be calculated by going from P to P0 prime and then from P0 prime to Q. But you note that that is of course the same as the work that you do to go from P to P0 to Q. This result, being independent of the path, cannot depend on the point P0 or the state P0 that we have chosen arbitrarily. Now, this actually tells us only the change in U is physically meaningful and not its actual value. The actual value depends on the arbitrarily chosen state P0. But as far as thermodynamics is concerned, that P0 could be a completely arbitrary choice. Changes in U, on the other hand, does not depend on your arbitrary choice. Now, using this definition of U, the first law now takes this form. Delta U is minus W adiabatic, or delta U plus W adiabatic is 0. This is of course for a finite change. For an infinitesimal one, we will have to note that in general d cross W is not an exact differential. That is exactly why we have a cross on the d here. to show that there is no function W in general whose differential the infinitesimal amount of work done in an infinitesimal process is. However, what the first law has told us is that under adiabatic conditions, this is d cross is actually d. So we have written dw adiabatic, and this is an exact differential. So what we wrote here in terms of finite transformations in the language of infinitesimal changes, this essentially is nothing but the statement that there is a function u which makes dw adiabatic an exact differential, that is a differential of a function, and you define u by saying du is minus dw ad. The minus sign again arises from the same reason as before. And it should remind you of the mechanics law that dv is minus f dot dr. And this of course integrates to delta u equal to minus w adiabatic, which is exactly what we have already said is the first law of thermodynamics in the language of internal energy. Now this has an interpretation, and this interpretation involves conservation of energy. What you would say is U, the internal energy of the system, is energy stored somehow in the system. And during an adiabatic process, the system uses up its internal energy to do work. So whatever work it does decreases its internal energy. Hence delta U equals minus W adiabatic, or delta U plus W adiabatic is 0. Note that from a microscopic point of view, the internal energy can be interpreted as a sum total of the energies of all the particles making up the system. But as far as thermodynamics is concerned, such an interpretation is not necessary to understand what is going on. Let me remind you once again, thermodynamics, at least the classical version of it, does not care about what's happening inside the system. What exactly is the structure of the system? It would work perfectly well without any idea about the microscopic world. Now, this brings us to our next important point. Now, in the microscopic world, the energies that the particles have are quantized, and you have energy levels, and the particles essentially have wave functions or states which tell you what the energy levels are. And what happens when you do external work is that you change the boundary conditions involved in the system. For example, when you move the walls, the system becomes larger, so the wave functions that are used to describe the system has to extend over a larger region. Now, this change in energy levels manifests in the change in total energy of the system. But as I've said, in thermodynamics, you don't really care about, or you don't have to care about this. You can live perfectly well without being aware of this microscopic picture. Now, because the first law of thermodynamics is an energy conservation statement, you would naturally ask what happens to it when you are no longer working under adiabatic conditions. If the same state change takes place when the system is not enclosed by adiabatic walls, then the work done will not be equal to the adiabatic work done in general. Note that in general the work done is path dependent, so if you are going to use a different path to go from PIVI to PFVF, and usually if it's not an adiabatic system, you would definitely use a different path from when the system were adiabatic. Then W and W adiabatic is different, so delta U plus W now is not equal to delta U plus W adiabatic. It's no longer 0. So the conservation of energy picture that we used so far, that whatever internal energy is in the system, that gets used up to do work, that will no longer be useful here. Now, this would make the conservation of energy break down unless we can invent a new kind of energy which balances things out here. And that's exactly what we do. We say that delta U plus W adiabatic was 0 because there the only source of energy was external work, and so the only way the system could also influence the external world was via doing work, and it was doing that at the expense of its own internal energy. However, if there is some other means by which energy can come into the system, and that is of course a kind of means that's available only if the walls are not adiabatic. Remember, that is what our basic condition is here. Then what you will have is that this new kind of energy will come in, and that balances out the books for you. So this is one kind which enters into the system only if the walls are non-adiabatic, and we call this new kind of energy heat. And this gives us the most well-known form of a consequence of the first law. In fact, many textbooks even refer to it as the first law. And this may be the form in which you know the law, which is delta U plus W equals Q. Q is a form of energy which comes in through diathermal walls, and it can either go to increase the internal energy, or a part of it can go in making the system do work. This is of course a version of conservation of energy where you have taken into account the fact that other means of energy transfer are available to you when the walls are no longer adiabatic. Now of course, textbooks which denote work done on a system by W would state this differently. They will say the delta U is Q plus W. Of course, there the idea is Q is energy coming in via non-work means, and W is energy coming in via work means. Both are energies input to the system, so both of them go to increase the internal energy. In our version, where we are using work done by the system as positive, then essentially W is output of energy and Q is input, which is why delta U in our version is actually Q minus W. Now the infinitesimal process version of this equation is simple. It's du plus d cross W. Note that we are back to using d cross W now that we are no longer under adiabatic conditions. The infinitesimal work done is no longer an exact differential. But du plus d cross W is equal to something else which is also definitely not an exact differential, d cross Q. The infinitesimal amount of heat flowing into the system. Let me also stress that although for work done, different textbooks use different conventions, that is, work done on the system is taken to be positive by some and work done by the system is taken to be positive by others, like we are doing here. For Q, the convention is much more universal. Heat flowing into the system is taken to be positive. So if heat flows out of the system, then Q is negative. Now, in the case of a hydrostatic system, in particular, a closed hydrostatic system, one in which the amount of substance does not change during a process, the infinitesimal heat absorbed is simply given by du plus pdv. Note that this version is independent of whether you choose work done on the system to be positive, or, as we have done here, you choose work done by the system to be positive. If you chose the latter convention as we have done, then the hydrostatic work done would be plus pdv, and as in this case, you are going to end up with du plus pdv for d cross q. On the other hand, if you had chosen work done on the system to be positive, then d cross w would have been minus pdv, but then again d cross w would not have been sitting on this side of the expression, it would have been on the other side, as we explained a while ago. So then you would end up with d cross q minus pdv being equal to du, which is of course the same as this expression. So this version is the same no matter which convention you are using. Now, Up to this point, the concept of heat may seem much like a bookkeeping device. Your internal energy change, your work done under adiabatic condition being equal to the decrease of the internal energy, was perfectly consistent with conservation of energy. You could just use the fact that internal energy of the system was being used up by it in order to do work. And the moment the walls enclosing the system become non-adiabatic, this simple story no longer works. So in order to keep energy conservation intact, you had to invent this new concept of heat. Now, put that way, this may really sound a bit of a trivial thing. The real significance of heat comes out fully when we talk about the second law, as we will later on in this course. However, even within the limits of the first law of thermodynamics, heat actually acquires an identity beyond just being something which is being used to sort of maintain energy conservation here. This identity is primarily due to the fact that when a system interacts with the surrounding, the amount of heat which the system absorbs and the amount which the surroundings absorb are related in a very simple fashion, something which we often call the first law of calorimetry. Let us now turn to see what that is. In order to understand this better, let us take a look at a schematic diagram where we indicate the fact that a system, marked here in green, is interacting with the surroundings which are marked here in blue. And we assume that the system and surroundings together form an isolated system. The two together do not interact with anything outside. Of course, if the surroundings in turn interacted with something outside, we could have taken that into the surroundings until the surroundings had nothing further to interact with. Note that for the system here, the amount of heat going in is being shown by this red arrow, and it's mentioned that this is Q sys for system. The arrow points inwards because, as we have seen, our convention is always heat entering inside is positive. That is, energy coming in the form of heat is to be taken as positive. On the other hand, the work arrow, W sys, this is the work done by the system, that is pointing out because that essentially indicates an energy loss. Which is why change in internal energy of the system is Q sys minus W sys. Q sys is the input, W sys as the output. However, in addition to that, I have also shown the same quantities with respect to the surroundings. There is W surroundings, which is actually pointing outwards from the surroundings and hence into the system, and Q surroundings, which are going into the surroundings away from the system. But note that from pure mechanics, it's very easy to see that whatever work the system does on the surroundings does exactly the opposite amount of work on the system. Well, from a mechanical point of view, you could simply say that this is the manifestation of Newton's third law. Whatever force one exerts on the other, its reaction is exerted by the other on the first one. And since the forces are equal and opposite, and whenever the system gets displaced, so does the surrounding, the work done have to be opposite to each other. Exactly. So W sys plus W surroundings is 0. But let us now note that the first law of thermodynamics applied separately to the system and the surroundings tell you that delta U of the system is Q system minus W system and delta U surroundings is Q surroundings minus W surroundings. And when you add these two together, you must get 0 because delta U system plus delta U surroundings is the increase of the overall universe, so to speak, the system plus the surroundings. We call this the universe not because we are imagining that everything in the universe is contained here. We call this the universe because it is self-contained. It does not interact with anything on the outside. Since it does not interact with anything on the outside, it does no work on the outside, and there is no heat coming in from the outside. So the larger system, which you get when you combine the system and the surroundings, must have a total energy which is unchanged. But now, if you add the two equations for expressing first law, one for the system, another for the surrounding, you immediately get from these facts that Q system plus Q surroundings must be zero. Whatever heat is gained by the system must be lost by the surroundings, or vice versa. Now, the reason why this result is exceedingly useful is basically that very often either the system or its surroundings may be such a system where keeping track of how much heat it is gaining or losing may be rather simple. Something which has a well-defined heat capacity, so to speak. We are going to talk a lot more about heat capacity later, but basically the real reason why this is so useful is maybe the surroundings has some easily measurable parameter which will tell us how much heat it is either gaining or losing. And by using that, you can easily figure out how much heat a system which is in contact with that is gaining or losing. And this is why this is called the basic law of calorimetry. That if there are no other places where energy can be transferred, that is, if the system and surroundings together really form an isolated system, then heat lost by one must be equal to heat gained by the other. Something which we have perhaps learned from our school days. One classic experiment in thermodynamics which used this notion of heat lost equal to heat gained very, very effectively was carried out by one of the founding fathers of the subject, James Prescott Joule. He actually happened to be a brewer by profession, but spent most of his spare time trying to devise ways of understanding heat, work, and surrounding various other topics, and it was mainly his effort which made thermodynamics into a very, very important part of the Industrial Revolution. Now, here we are going to describe a particular experiment which Joule carried out. This was his experiment on the free expansion of a gas. So here you have a gas in a particular system, in a flask. And this flask is connected to another flask which has been evacuated, but the two are connected through a stopcock which is right now switched off. So you have gas on this side, vacuum on the other. In Joule's experiment, this entire setup was submerged in a body of water, and there was a thermometer which was placed in the water. Now what Joule observed is that if we were to turn the stopcock and allow the gas to expand freely into the vacuum, then after everything settled down and the gas sort of reached equilibrium on both sides, the temperature of water as measured by his thermometer showed no change. Now, what he could conclude from that is, first of all, the temperature of the gas before and after the free expansion is the same. But a more important conclusion could be drawn in terms of the internal energy change in the process. For this, you will have to note the following. Here the gas is expanding freely. There is no force to hold it back. So even though its volume is increasing, it does not really have to do any work. Note that here PDV is not a valid thing to use if you think of P as the pressure of the gas. In any case, in the intermediate stages of this process, once you have opened the stopcock and until gases on the two sides reach equilibrium, you can't even talk of a well-defined pressure of the system. This is as far away from a quasi-static process where intermediate stages are close to equilibrium states as possible. So here P equal to P external does not hold, and as a result, the work done has to be calculated using the external pressure. And the external pressure being 0, here you do not have any work. Now, the next part uses the heat loss equal to heat gained idea. Since the water temperature does not change, we can use that to deduce that it would not lose any heat. And since whatever heat the water loses, in this case none, is the amount of heat the system, in this case the gas, gains, it must follow that no heat flows into the gas. Now, an immediate consequence of this was the following. You have a process of free expansion. You had a gas in a small volume and, of course, large pressure before. Now you have a gas which is spread out over a much larger volume, lower pressure. But in this process, no work has been done and no heat has been exchanged. So this tells you that free expansion of a gas is an adiabatic process. And what does it tell you about the internal energy change? Change in the internal energy must be equal to Q minus W, and that's 0 minus 0, so it's 0. In other words, the internal energy of a gas does not change with its volume if its temperature stays fixed. So in more mathematical terms, what we can say is U is a function of temperature and temperature alone. And as a result, if you did calculate the partial derivative of U with respect to the volume at a fixed temperature, del U del V at constant T, and of course constant N, which we are not mentioning any longer, but remember we have already decided that unless otherwise mentioned, all our systems will be at a constant number of moles. So del U del V at constant T and N is 0. So this is a basic defining property of an ideal gas in thermodynamics. One of them is PV equal to nRT, the so-called mechanical equation of state, which of course could be obtained using real gases, but under situations where a real gas closely mimics an ideal gas, that is low pressure, high temperature situations. But this is not enough to define an ideal gas. The other result that you need in thermodynamics to define an ideal gas is U is a function of T alone. Which particular function of T? Thermodynamics really is silent about that. In order to figure out which particular function this is, you have to go in for something more fundamental or something more microscopic. But we are not going to go into that, at least not right now. Now, let me point out a very important thing. This result that Joule obtained made many calculations using gases, ideal gases, very, very simple, and that actually allowed people to verify their experimental results with theory much better than before. But the important point is Joule had not experimented with an ideal gas. In reality, there are no ideal gases. So his gas, of course, was a real gas. In fact, his gas was nothing but air. And in actuality, the temperature did change a bit in the measurement. But Joule did not have measuring instruments, thermometers, which were accurate enough to detect this. This was very, very lucky. As far as the history of thermodynamics is concerned, this simple fact that Joule did not have nice enough instruments, the kind that we have in labs today, allowed him to actually arrive at this very nice description of an ideal gas, that in addition to PV equal to nRT, it also obeys U is a function of temperature alone, which in turn led to a large amount of advancement in the subject. In the next lecture, we will explore this idea of heat and related concepts like heat capacity in a bit more detail. Till then, bye.